Okay, so welcome back. Now, in this example, we're looking at a sequence that is defined recursively. Okay, so how would we handle something like this? Well, let's read through it carefully. It says we have a sequence a sub n defined recursively such that a1 is 2, and then a sub n plus 1 is defined by this formula for all n greater than or equal to 2. Okay, so now, first thing we do is write out some of the sequences. And one thing I notice is, again, the first term is 2, but look at all the other successive terms. Notice that the numerator is 1 more than the denominator. So I would conjecture that, I would form a conjecture or a conjecture that this is bounded below, or excuse me, yeah, bounded below by 1. Okay? But again, that's a conjecture. How do we show this? Well, we want to show that the sequence is greater than or equal to 0, or excuse me, greater than or equal to 1. Okay? So that's what we need to show. Okay, so let's start with without the 2, let's start with this. And so we have to show excuse me. So we want to show that a sub n over 2 plus 1 over 2 times a sub n is greater than or equal to 1. That's what we want to show. Okay, so what I'm going to do is rewrite this as a common denominator. So I'm going to write this as a sub n squared plus 1 over 2 a sub n. And that's going to be greater than or equal to 1. Okay. Now also notice that what we have here is our positive term. So we notice that a1 is positive, and all successive terms are formed by adding positive terms or positive numbers. So it looks like we can see that all the terms are going to be positive. Okay. Now, similarly, all the terms are greater than 0, right? So there's all going to be positive terms. All of the terms are going to be positive. And so what do we get? Well, if we have this, right, so this is what we want to show. Okay, so this is what we want to show. We know that since this is positive and this is the way this is defined, we're taking 2 positive numbers, so this is going to be positive. And basically every term is going to be the sum of positive numbers. So we know that a sub n is positive for all n greater than or equal to 1. So that means that this is going to be greater than or equal to 1 if and only if, okay? So a sub n squared plus 1 over 2 n will be greater than or equal to 1 if and only if what? If a to the n squared plus 1 is greater than or equal to 2 times a sub n. Okay, now why do we need to know that these are all positive in order to do that? Well, because if we know that all the terms are positive, and this is always going to be positive, then when we multiply both sides by a sub n, we can keep the inequality the same direction. Okay, so that's why it's if and only if. So since we know that all the terms are positive, and this is going to be positive, right? Then we can multiply both sides by 2 a sub n, and now we have to show this. Okay, now, where do we go from there? Well, let's rewrite this inequality, and let's subtract from both sides. So let's rewrite the inequality like so. So this is going to be a sub n squared minus 2 times a sub n plus 1 is greater than or equal to 0. Now notice that this here is a perfect square in a sub n, right? So we could rewrite this as a perfect square. So this would be a sub n minus 1 quantity squared is greater than or equal to 0. Okay, so now, as we know, any non-negative, right? Any real number is non-negative when it's squared. So we know that the fact that any real number, right, that is squared is going to be non-negative, which means this is automatically true. We know this is true for all real numbers, even though we're not talking about all real numbers. But for all real numbers, any real number squared is going to be greater than or equal to 0. So this is automatically true for all n, which gives us our result, our conclusion. So therefore, since we just showed that this is always true, well, then that means we just showed that this is true. So therefore, we have our conclusion. an over 2 plus 1 over 2 a sub n is greater than or equal to 1. Okay. So now we just showed that it's bounded from below by 1. Okay. Yeah, let me do this. Okay. So we just showed that it's bounded below by 1. Okay, good. Now what do we need to show? Now we need to show that it's decreasing. So we got it bounded below by 1. Now we just need to show that it's decreasing, and we can use the monotone convergence there. Okay. So that means we need to show that a sub n plus 1 is less than or equal to a sub n for all n, okay, for all n greater than or equal to 1. Okay, so how do we do that? Okay, now, since a sub n squared is greater than or equal to 1, right? And that comes from the fact that for all real numbers, the square that we saw in the that I erased, a sub n squared minus 1 squared is always greater than or equal to 1. And so since this is greater than or equal to, since a sub n squared is greater than or equal to 1, or excuse me, greater than or equal to 0, that's what it was, I'm sorry. So remember, we showed that a sub n squared minus 1 was greater than or equal to 0. So since a sub n squared is greater than or equal to 1, okay, then it follows that a sub n squared right? So again, this is just coming back from the fact that what we did before. So I'm going backwards, right? So we started here, okay? And since this is greater than or equal to 1, then it makes sense that this is, hold on a second. Oh, I'm sorry, I wrote this wrong. Got it backwards. Since this is greater than 1, I'm going to add a sub n to both sides. So if I add a sub n to both sides, then it naturally follows that 2 times, hold on, 2 times a sub n is greater than, oops, hold on. Yeah, that's right. 2 times a sub n is greater than or equal to a sub n plus 1. Okay, that's what I wanted. Okay, so if this is true, so since this is true based on this, then it follows this must be true, right? Because all I did was add a sub n, oops. Hold on a second. Yeah, that's right. So yeah, all I did was add that's not going to work. How am I doing? Oh, yeah, I'm sorry. That's right. A sub n squared, right, to both sides. There we go. Sorry about that. So I'm just adding a sub n squared to both sides. That's what I'm doing. So since this is true, then obviously this is true. Okay, so that's where I wanted to be. So now, what can I do here? So where does this get us? Well, what am I trying to do? I'm trying to get to here. So, what do I need? Well, I want a 1 over 2a sub n here. And I've got an a sub n here, I've got an a sub n squared. So if I divide both sides, by 2a sub n, what does that get me? Well, I think that does it. So that gives me what? Well, if I divide this, I get a sub n, which is what I was looking for. And over here, well, what does this become? Well, this becomes a sub n over 2 plus 1 over 2 times a sub n. And what is this? Well, this is just a sub n plus 1. And I think that's it. Okay, that's it, yeah. So this shows that a sub n is greater than or equal to a sub n plus 1, which is what we wanted to show. And so therefore, by the monotone convergence theorem, because this is a decreasing sequence and it's bounded from below, in this case by 1, that the sequence converges. Okay, now, the next step is figuring out what does it converge to. Okay, so now that's going to be interesting. So let's talk about that. Okay, so now we need to figure out where this thing converges. Since it does converge, right, we want to find the limit, right? So we need to find the limit L that equals, the real number L that equals the limit as n approaches infinity of a sub n. Okay. Now we're going to use the recurrence relation. Okay. And don't forget, just like in the last one, remember, this is equal to this, which is also equal to this, right? So now, which is equal to what? Which is equal to the limit as n approaches infinity of what? Well, it's the limit of a to the n 2 plus 1 over 2 a to the n, right? Okay, so now, well, what does this equal? Well, this equals what? Well, again, the limit of a sub n is L, right? And we're using the fact that this limit is equal to this limit, which is equal to this. Well, a sub n, well, again, I'm going to use the limit laws. And I'm going to say that this is the limit of a sub n over 2 plus 1 over 2 times the limit as n approaches infinity. Oh, let me rewrite that. Write this a little bit better. So limit as n approaches infinity of a sub n over 2 plus 1 over the limit as n approaches infinity of, 2 times the limit, so this would be a sub n. So now we got that. Well, we already know that this limit is L, so what do we get? We get L over 2 plus 1 over 2L. Okay. Well, guess what? Now we've got an expression that we need to solve. So now we've got this is equal to L. So now if we simplify this, we got L is equal to what? L plus 1, L squared plus 1 over 2L. Which then gives me what? L, so it's going to be 2L squared equals L squared plus 1, which then gives me a quadratic in L. So what do we get? We get 2L squared minus L. Oh, hold on a second. Yeah, this is right. I'm sorry, not it. So I gotta subtract from both sides. So this is going to give me L squared is equal to 1. And this tells me that L is equal to 1 and L is equal to negative 1. Okay, now, can only have one limit. So which one is it? Well, let's go back to what we said before. Remember, all of the terms are positive. And since all the terms are positive, the limit can't be negative 1. So the limit is 1. And we're done. Have a great day.